31 degrees Celsius. That is the temperature of the ocean water sitting right now beneath a broad, spinning mass of deep convection in the western Atlantic basin. Water so warm it reads like a heated bath rather than open ocean. On satellite loops, the system looks formidable. Cold, white cloud tops flaring 6 kilometers into the atmosphere, wrapped around a distinct upper-level rotation that looks for all the world like a fully formed tropical cyclone. But if you call Environment and Climate Change Canada or the meteorologists at the Canadian Hurricane Center in Dartmouth, they will tell you something that sounds almost paradoxical. As of this evening, this massive weather feature does not have a name. It is not a hurricane, and officially, it is designated as nothing more than an area of interest. That gap, the vast distance between what this atmospheric feature looks like on space-based radar and what it physically is at the sea surface, is where the real story begins. Headlines across North America have already started using the word storm, selling the immediate visual drama of a swirling vortex. But the headline framing is loose, and correcting it is critical. What is sitting off our continental coast right now is not a tight, destructive core. It is a top-heavy, disorganized disturbance. It possesses an abundance of upper-level spin and an extraordinary ocean heat reservoir beneath it, but it lacks the single structural element required to turn a weather system into a named threat, a closed, low-level surface circulation. In the penthouse of the atmosphere, 6 kilometers up, the system is turning. In the basement at sea level, where energy must be drawn from the ocean, the winds do not meet. It is empty where it matters most. And understanding that precise structural failure, why a system with every raw thermodynamic ingredient can remain stalled in atmospheric limbo, is a far more compelling story than simple clickbait warnings. It exposes the delicate physics of tropical cyclogenesis, where a single missing variable determines whether a system remains a heavy rain event or transforms into a continental hazard. For Canadians, atmospheric systems in the Atlantic Basin are never an abstract, distant concern. The Canadian Hurricane Center in Dartmouth continuously tracks these tropical precursors because the atmospheric rivers and steering currents that guide them routinely map out paths directly toward the Atlantic provinces, driving extreme rainfall across Nova Scotia, Newfoundland, and New Brunswick, or impacting eastern Canadian shipping lanes. Whether a disturbance stays disorganized or locks its basement circulation into place dictates whether severe weather alerts will eventually sound across eastern Canada. The National Hurricane Center in Miami and meteorologists in Dartmouth currently assign this system a low 30 to 40% probability of developing into a named tropical depression over the next 48 hours. That number reflects genuine atmospheric indecision. The thermodynamic recipe is present, but two invisible steering currents are actively pulling the disturbance in opposing directions, creating an atmospheric tug-of-war. This entire investigation answers one central question. What specific structural piece must click into place over 31-degree water for this disorganized rotation to lock down to the surface? And which stretch of the North American coastline sits at the terminal end of the current it ultimately decides to ride? A single temperature reading on a surface drifting buoy, 31.0 degrees Celsius. In the historical archives maintained by Environment and Climate Change Canada and international ocean monitoring networks, that number represents a baseline anomaly that shatters decades of recorded marine data for early season basin temperatures. To understand why an unorganized cluster of rain showers off our continental margin is causing such intense evaluation at the Canadian Hurricane Center in Dartmouth, you have to look at the baseline physics that governed Atlantic tropical systems for the past century. Oceanographers and atmospheric scientists have long established that the thermodynamic threshold for tropical cyclogenesis is 26.5 degrees Celsius. Below 26.5 degrees, the surface waters lack the thermal energy required to drive rapid evaporation and sustain deep convective updrafts. At 26.5 degrees, the ocean provides just enough latent heat to act as a functional atmospheric engine. When historical storms like Hurricane Juan in 2003 or Hurricane Fiona in 2022 tracked northward toward Canadian territorial waters, their life cycles were defined by how long they could sustain themselves over waters meeting or exceeding that baseline before encountering the cooler, stabilizing marine layers of the northern Atlantic. Historically, early-season basin water temperatures sat comfortably within a predictable normal range, typically hovering right around 27 to 28 degrees Celsius across the warm southern reservoirs, and cooling rapidly as you move north. That baseline gave forecasters a clear, mathematically grounded boundary. Systems forming early in the summer season were structurally constrained. They lacked the shear thermal surplus required to overcome atmospheric headwinds like dry air or moderate wind shear. To quantify what 31.0 degrees Celsius actually means, consider the scale translation of ocean heat content. A single cubic kilometer of seawater heated to 31 degrees Celsius holds an exponential surplus of thermal energy compared to the baseline 26.5 degree threshold. Across thousands of square kilometers of open ocean, that thermal surplus represents a massive kinetic battery. It converts the upper 40 to 50 meters of the sea into an uninterrupted power grid for atmospheric convection. When air flows over seawater at 31 degrees, the evaporation rate surges, saturating the boundary layer with immense quantities of water vapor. As that saturated air rises 10 to 12 kilometers into the troposphere, it condenses, releasing latent heat of condensation at an astounding rate. This latent heat release warms the surrounding column of air, making it lighter, which causes surface pressures to plummet. Lower surface pressure draws in more surrounding air, accelerating surface winds and creating a self-sustaining thermodynamic loop. Historically, when forecasters at the Geological Survey of Canada or Environment and Climate Change Canada evaluated historical weather baselines, early-season systems rarely had access to deep ocean heat of this magnitude. When a young disturbance lingered over water in previous decades, its vertical updrafts would churn the ocean surface, bringing up cooler water from 40 meters down, a process known as upwelling. That upwelled cool water acted as a natural internal brake, choking off the storm's fuel supply and preventing runaway intensification. But current bathymetric and thermal profiling shows that this 31-degree heat layer is not just a thin surface skin. It extends deep into the upper water column. The natural internal brake has been temporarily disabled. This historical departure is precisely why the current monitoring protocol is so rigorous. When the Canadian Hurricane Center tracks Atlantic developments, they compare real-time microwave satellite imagery and sea surface temperature grids from Ocean Networks Canada against 50-year historical averages. The current reading sits more than 2.5 degrees Celsius above the historical median for this time of year. In fluid dynamics and atmospheric physics, a 2.5-degree positive anomaly over a continuous body of water is not a minor fluctuation. It is a fundamental shift in the boundary conditions of the system. The tension today comes from a direct clash between historical probability and physical potential. Historically, a disorganized area of interest facing upper-level wind shear and dry continental air would simply dissipate within 72 hours. The baseline data told us that weak surface centers cannot survive those headwinds. But historical baseline data assumed ocean temperatures of 27 degrees, not 31 degrees. With rocket fuel sitting in the sea surface, the margin for error in atmospheric modeling vanishes. To track where this historical anomaly leads, meteorologists are watching three precise baseline indicators over the next 12 hours. First, whether surface pressure drops below 1,008 millibars at central buoy stations. Second, whether low-level wind vectors close into a complete 360-degree loop around a single point. And third, whether the Canadian Hurricane Center upgrades the system's development probability past the 50% threshold. Until those specific physical markers occur, the system remains an unformed threat sitting on top of an unprecedented thermal reservoir. At 1800 UTC, three separate instrument platforms across the western Atlantic basin, a drift buoy reading, a microwave satellite pass, and an automated surface weather station, registered three distinct anomalies that resolved into a single physical reality. The atmospheric pressure column above 31-degree water had begun to decouple from the mid-level circulation. The surface reading showed a pressure of 1,004.8 millibars, while 8 kilometers overhead, an upper-level trough was accelerating wind vectors in the exact opposite direction at 45 knots. To the untrained eye looking at dramatic infrared loops, this appeared to be a rapidly spinning storm system. But to atmospheric scientists evaluating real-time telemetry at the Canadian Hurricane Center in Dartmouth and Environment and Climate Change Canada, the data revealed the exact opposite mechanism: a system structurally choked by shear, actively preventing its thermodynamic engine from turning over. The sensationalized headline accounts frame this event as a runaway hurricane in the making, but correcting that framing exposes a far more intricate scientific mechanism. The accurate phenomenon is a stalled convective heat engine caught in an extreme environmental conflict. On one side, you have an unprecedented thermal reservoir offering unlimited latent heat. On the other side, you have vertical wind shear and dry air intrusions acting as atmospheric shears, slicing off the top of the convective stack before it can lock down to the ocean floor. The real drama is not whether 31-degree ocean water has energy, it obviously does, but whether the physical architecture of the atmosphere will allow that energy to consolidate into a focused vortex. Here is how the thermodynamic engine physically works, step by step, without the distraction of media adjectives. A tropical storm is fundamentally a heat engine operating between two thermal reservoirs, the warm ocean surface at 31 degrees Celsius and the extremely cold upper atmosphere, roughly 12 kilometers up, where temperatures drop to minus 60 degrees Celsius. Warm, humid air rises off the sea surface because it is less dense than the cooler air above it. As it ascends, the water vapor expands and cools, reaching its dew point. At that exact altitude, condensation occurs, forming deep convective thunderstorm chimneys. Condensation releases latent heat of vaporization, the energy that was stored in the water when it evaporated from the sea. This released heat warms the surrounding air inside the cloud column, making it even lighter, which forces it to rush upward at speeds exceeding 30 meters per second. As millions of tons of air rush upward into the upper atmosphere, a vacuum is created at the surface. Pressure at sea level drops. Air from surrounding areas rushes inward toward this low-pressure zone to fill the void. But because the Earth is rotating, the Coriolis force deflects this incoming air to the right in the northern hemisphere, causing the incoming surface winds to spin. If the atmospheric column is aligned vertically, this spinning air spirals tightly inward, accelerating like an ice skater pulling in their arms. The central pressure plummets further, drawing up even more moisture from the 31-degree ocean, creating a closed, self-sustaining thermodynamic loop. This is tropical cyclogenesis in its pure, unobstructed state. What has broken the traditional modeling today is the sheer magnitude of the environmental conflict. The historical computer models, built on decades of atmospheric observations gathered by meteorologists and fluid dynamicists, were calibrated under the assumption that high vertical wind shear of 25 knots or more would reliably destroy a weak disturbance. Vertical wind shear is the difference in wind speed and direction between the sea surface and 10 kilometers altitude. When shear is high, upper-level winds blow the top of the thunderstorm chimneys dozens of kilometers downstream from the surface center, like smoke being blown away from a smokestack. This disrupts the vertical alignment, prevents latent heat from concentrating over a single point, and allows dry air from the middle levels of the atmosphere to entrain into the system. Dry air acts as an evaporative sink. When rain falls into dry air, it evaporates, cooling the air rapidly and creating powerful downward drafts of cold air, downdrafts, that slam into the sea surface and destroy the low-pressure center. However, the 31-degree ocean water introduces an unprecedented counterweight. The evaporation rate off 31-degree water is so extreme that the latent heat output from the convective chimneys is generating massive moisture plumes that actively fight back against dry air entrainment. The thermal battery is attempting to overpower the mechanical shearing forces. This explains why traditional forecast models are oscillating so wildly. Their algorithms are caught in a mathematical tug-of-war between high shear mechanics that dictate destruction and extreme latent heat flux that dictates rapid intensification. The evidence confirming this shift comes directly from advanced sensor networks. High-resolution microwave sounders aboard polar orbiting satellites, monitored continuously by Environment and Climate Change Canada and international partner agencies, show that while mid-level dry air is invading the western quadrant of the disturbance, the low-level moisture flux remains at near-record levels. Ocean Networks Canada's offshore array and deep-sea profiling buoys confirm that upper ocean heat content, the actual volumetric heat stored in the top 50 meters, is high enough to sustain a Category 2 hurricane if vertical alignment is ever achieved. To understand how this balance resolves, watch 3 specific operational markers over the coming hours. First, whether surface anemometers at offshore monitoring stations register a closed circulation vector with sustained winds exceeding 39 knots. Second, whether dropsonde soundings from reconnaissance flights show mid-level relative humidity rising above 75% near the core. And third, whether the Canadian Hurricane Center issues a technical bulletin placing Atlantic coastal zones on formal watch. Until one of those physical thresholds is crossed, the system remains a massive thermodynamic engine trapped in mechanical friction. A red emergency banner across a screen in Halifax at 7:15 Atlantic time. A flash flood watch covering 120 millimeters of rain over 24 hours, issued before the system even has a name. That single mobile alert from Public Safety Canada's Alert Ready system illustrates the real-world escalation. The public conversation centers on whether a storm will make landfall as a named hurricane with destructive winds. But that framing overlooks the actual mechanism of damage. The accurate reality is that an unorganized, slow-moving tropical disturbance carrying extreme moisture poses a severe, immediate infrastructure threat long before it ever qualifies for a formal name. The true danger of a stalled system is not wind. It is moisture volume, duration, and infrastructure saturation. When a disorganized convective mass sits over 31-degree water and meanders along a stalled steering front, it acts as an atmospheric conveyor belt. Instead of moving quickly across the map at 30 kilometers per hour, it locks into place, pumping tropical moisture into high-altitude winds that funnel directly toward North American landmasses. For Canadian communities along the Atlantic seaboard and inland river valleys, this mechanism creates a compound disaster scenario. When hundreds of millimeters of rain fall onto already saturated watersheds over 48 continuous hours, the physical infrastructure designed during the 20th century begins to fail systematically. Consider scale translation to understand the volume of water involved. If this system discharges 150 millimeters of rain over an area of 10,000 square kilometers, an area roughly twice the size of Prince Edward Island, it drops 1.5 billion cubic meters of water onto the landscape. That is equivalent to dumping the entire annual residential water consumption of a major metropolitan area onto a single river basin in 2 days. Soil absorbs water up to a physical threshold called field capacity. Once that capacity is breached, 100% of subsequent rainfall becomes surface runoff, cascading directly into drainage networks, culverts, and river channels. In eastern Canada, the real-world consequences manifest in specific critical supply corridors. When torrential tropical plumes hit the regional topography, small coastal rivers exceed their banks in hours. We saw this structural failure during the atmospheric river events of November 2021 in British Columbia, which severed every major highway and rail line connecting the Port of Vancouver to the rest of Canada, causing billions of Canadian dollars in supply chain disruption. A stalled Atlantic disturbance running up the eastern seaboard threatens an identical cascading failure. Key transportation arteries like Trans-Canada Highway route segments, rail links through low-lying river valleys, and port facilities face immediate inundation. Beyond transportation networks, energy and civil infrastructure sit directly in the line of escalation. Modern electrical distribution systems, such as those managed by Hydro-Quebec or Nova Scotia Power, are built to withstand predictable seasonal wind loads. But when extreme rainfall destabilizes the soil matrix around transmission towers and utility poles, even moderate wind gusts of 60 to 80 kilometers per hour can overturn heavy infrastructure, triggering wide-scale power outages. In municipal centers, storm sewer networks designed for historical 50-year rainfall events are overwhelmed instantly. Backflow valves fail, urban basements flood, and municipal water treatment plants are forced to bypass untreated effluent directly into local harbors and rivers to prevent plant destruction. For ordinary daily life, this shift alters everything from emergency management protocols to economic stability. When Public Safety Canada issues localized advisories via the Alert Ready system, municipal authorities are forced to execute emergency response plans on short notice. Ferry services across the Cabot Strait linking Nova Scotia and Newfoundland face multi-day cancellations, severing primary freight routes for fresh produce and medical supplies. In rural communities, agricultural land faces soil erosion and crop loss valued in the tens of millions of Canadian dollars, while residential property insurance premiums across coastal provinces surge to reflect the newly calculated baseline risk. The escalation is not a hypothetical future scenario. It is an active physical process being measured hour by hour by the Canadian Hurricane Centre in Dartmouth and Environment and Climate Change Canada. The key to tracking how this escalation unfolds over the next 24 hours relies on watching three specific infrastructure and environmental checkpoints. First, weather river gauge telemetry from the Water Survey of Canada shows stream flows rising past historical flood stages in coastal watersheds. Second, whether Public Safety Canada issues formal evacuation orders or highway closure alerts for low-lying transit corridors. And third, whether the Canadian Hurricane Centre upgrades the system's designation from a heavy rain warning to an active tropical storm alert. Until those operational thresholds are crossed, the situation remains a slow-motion hydrologic threat anchored over an ocean battery. A single pressure trace recorded by an automated sea buoy at 2100 UTC, 1002.4 millibars, fluctuating by less than 0.2 millibars over 3 consecutive observation hours. That motionless barometer line is where the atmospheric drama culminates tonight. Sensational headlines continue to frame this system as an imminent catastrophe or a media exaggeration. But the accurate reality is far more subtle and technically precise. We are witnessing an atmospheric standoff, an unresolved thermodynamic test case occurring over 31-degree water. The honest boundary between what is established science and what remains genuinely unknown is precisely what defines credible forecasting. And defining that boundary is where we end this analysis. What is conclusively established is the thermodynamic foundation. Deep ocean profiling from Ocean Networks Canada and satellite sea surface temperature grids confirm that 31 degrees Celsius water extends 50 meters into the water column, holding an immense reservoir of thermal energy. We know with certainty that the moisture envelope surrounding the system is dense, that upper-level instability is high, and that latent heat of condensation is actively firing in convective chimneys 6 to 12 kilometers above the sea surface. The physics of the engine are real, verified, and operational. What remains genuinely unresolved is the mechanical consolidation. Atmospheric scientists at Environment and Climate Change Canada and the Canadian Hurricane Centre in Dartmouth cannot state with certainty whether the opposing steering currents will allow the system to dwell over open water long enough to close a low-level surface center, or whether wind shear will force a rapid drift onto continental landmasses before organization occurs. The computer forecast models, from the traditional European physics ensembles to the advanced artificial intelligence algorithms, are split across a wide spectrum of potential tracks, ranging from a weak, disorganized rain event over eastern North America to a Category 2 equivalent cyclone lingering in the offshore corridors. The atmosphere has simply not declared its hand, and claiming otherwise would be irresponsible. To know which path this system will take over the coming days, there are 3 specific checkable markers on the watch list that will tell you exactly how this resolves. First, watch the official bulletins from the Canadian Hurricane Centre in Dartmouth for the assignment of an invest or depression tag, specifically checking whether reconnaissance dropsondes report a closed surface wind loop of 360 degrees around a single pressure minimum. Second, monitor the high-altitude jet stream maps for the arrival of a northern trough, which would open a distinct escape route and pull the system northward toward Atlantic Canadian maritime routes. Third, check the public emergency broadcast feeds from Public Safety Canada's Alert Ready system for regional flood watches along coastal and river basins, which will indicate that atmospheric moisture plumes have locked onto land. Until one of those 3 checkable events occurs, the situation remains precisely what the telemetry shows: a massive, unformed thermodynamic engine suspended over an exceptionally warm ocean, waiting for the atmospheric architecture around it to shift. The danger of an unorganized storm is never just the wind it carries today, but the precedent it sets when 31-degree water becomes the baseline for the future. Let me know in the comments below where you are watching from tonight. If you value precise, authoritative documentary dispatches on planetary systems, hit like and